Okay, so why do we bother classifying chemical reactions? Okay, and the answer to that is, if you have several reactions and they all belong to the same class, the reactions will have some similarities between them. So if you know something about one of the reactions, you'll know something about the other ones. Okay, so it's very useful to categorize objects or phenomena into different categories. Okay, so let's take a look at our first one. Oops, sorry, didn't want O2 there. This is a very simple one. Okay, and we're going to balance this, reactants and products. So we write down the elements in the order in which they appear. Okay, and we're going to write down how many of each we have. So I have 1 sodium and 2 chlorines, 1 sodium and 1 chlorine. Oops, so why am I writing 2? All right, so the sodium's already balanced, need to balance the chlorines. So I'm going to put a 2 up here. Remember, we can only put coefficients in. So 1 sodium. Now, we're not just changing the chlorine, we're also changing the sodium. So 1 sodium times 2 is 2 sodiums. 1 chlorine times 2 is 2 chlorines. So now the chlorines are balanced, but not the sodium. So I need to put a 2 here. 1 sodium times 2 is 2 sodiums. 2, 2, 2, 2. So we're balanced. But as always, we go back and check. 2 sodiums, 2 sodiums, 2 chlorines, and 2 times 1 is 2 chlorines. Okay, so now we have this balance. All right, so what type of chemical reaction is this? Okay, this is what's called actually has 2 names. A synthesis. Synthesis means to make, or it's also called a combination reaction. Okay, and its general form is A plus B gives me AB. It's the general form of a synthesis reaction. Okay, now a synthesis or combination reaction is very, very easy to spot because it only has one product. Any reaction that has just one product, and all synthesis reactions have one product, any reaction that has one product is therefore a synthesis or combination reaction. Okay, synthesis or combination. And so easy to spot. And again, synthesis means to make. So we're putting things together and making one compound. Okay, any questions? All right. So now that we're all experts on synthesis reactions, let's look at the next category. When you're copying these down, you should leave a little space before each chemical, because you know the coefficient is probably going to go in there. Okay, so we're going to balance this. Reactants and products. Copy the elements down, Cu and Cl, and Cu and Cl. Okay, here I see 1 copper and 1 chlorine. Here I see 2 coppers, 2 different chemicals, 2 coppers and 2 chlorines. Okay, now, you should never begin when you're balancing. We did the balancing last week, but we have to do balancing for these reactions also. Never begin with a pure element. Okay, so we know that. So we're going to begin with the chlorine. Never begin with a pure element unless you have to. Also, copper is in 2 different chemicals on the same side. 2 different chemicals on the same side. So double whammy for copper. All right? So you never begin with a pure element, never begin with an element that's in two different chemicals on the same side. So we'll begin with the chlorine, 2 over here and only 1 over here. So all I can do is put a coefficient of 2 here, right? So that's 1 chlorine times 2 is 2, but it's also going to change to copper, Cu. 1 copper times 2 is 2 coppers. 2, 2, 2, 2. We're done. We're done. As always, you go back and check. 1 copper times 2 is 2 and 2 coppers. 1 chlorine times 2 is 2 chlorines and 2 chlorines. So we're done there. All right, so we have it balanced. So what type of reaction is this? Well, if you notice, it's the exact opposite of the synthesis reaction. All right, so this is what's called a decomposition reaction. Decomposition. All right, and what's the general form of a decomposition reaction? AB goes to A plus B. AB goes to A plus B. So notice here, synthesis reaction had 1 product. We had 2 or more chemicals coming together to form 1 product. Here we have 1 reactant breaking apart to form 2 products, right? So it's the exact opposite of a synthesis reaction. And again, just from the name, you should be able to kind of figure out what it is. When something decomposes, you have something that breaks apart, right? When something dies, when an animal dies, it breaks apart. Its legs fall off, its arms fall off. Okay, things decompose. A tree decomposes, the bark falls off, branches fall off, the leaves fall off, right? So that's what's going on here. We have something breaking apart into smaller pieces, right? So that's the general form of a decomposition reaction. And how do we spot a decomposition reaction? Extremely easy. 1 reactant. Synthesis has 1 product. A decomposition reaction has 1 reactant. Remember, it's been a while. The reactants are on the left side of the reaction arrow. The products are on the right side. So 1 reactant for a decomposition, 1 product for a synthesis reaction. Right? Again, they're the opposite of each other. Okay, any questions there? Any questions? All right, we'll move on to the next type then. Now, can a reaction be more than 1 type? Yes. All right, we'll see that later. Actually, each of those reactions was more than 1 type, but we haven't done the other type yet. Again, leave a little space before each chemical. Okay, as always, we're going to balance it first, reactants and products. All right, so here we have aluminum and chlorine and copper. Same order on both sides. For those of you that weren't here last week, same order on both sides. Okay, so now we write down how many of each we have. And let's see, I see 1 aluminum and 3 chlorines and 1 copper. 1 copper, 2 chlorines, and 1 aluminum. 1 aluminum. Okay, now, let's see. We had said never begin with a pure element. I have 2 of them here, copper and aluminum. Never begin with a pure element. So the only other element left is chlorine, and it is in fact not balanced. And for those of you that were with us last week, if you remember, when you have a situation like this where you have an odd number and an even number of the same element, an odd number and an even number, very easy. This is one of our 3 little tricks to balance a reaction quickly. The first is never begin with a pure element. The second, never begin with an element in 2 or more different chemicals on the same side. And the third is, if you have an element that has an odd number and an even number, find the lowest common multiple. To borrow a phrase from our math class, the lowest common multiple of 3 and 2 is 6. All right, so I'm going to want 6 chlorines on each side. So I need to put a 2 here and a 3 here. All right, 1 aluminum times 2 is 2 aluminums. 3 chlorines times 2 is 6 chlorines. Over here, I have 1 copper times 3 is 3 coppers. 2 chlorines times 3 is 6 chlorines. All right, So here I have the chlorines now balanced, the aluminums and the coppers are not. So let's do the copper first. Here I have 3 coppers, here I have 1, so I'm going to put a 3 here. All right, here I have 1 aluminum, here I have 2. So I'm going to put a 2 here. 263, 263. Okay, as always, we're going to check. For those of you that weren't here last week, sometimes you'll have these right, but they'll be the same, but you'll actually have made a mistake and it won't actually be balanced. You should always go back and check at the end. 1 aluminum times 2 is 2, 2 aluminums. 3 times 2 is 6 chlorines, 2 times 3 is 6 chlorines. 3 coppers, 3 coppers. So this is in fact balanced properly. Okay, so what type of reaction is this? Well, let's take a look here. If I can draw a line or an arc like this, okay, the copper has taken the place of the aluminum in the product. Oh, sorry, that was supposed to be a 3. I thought I erased that. Okay, so here the chlorine is with the aluminum, here the chlorine is with the copper. So the copper and the aluminum have traded places. This is what's called a single displacement. Actually, it has 2 names: single displacement or single substitution. Okay, and what's the general form? Well, the general form is okay, so why did I write those in different color? Notice, this is an ionic compound. It's got a metal and a non-metal. An ionic compound. Okay, so here, the metal cations are in blue, the anion, the non-metal anion chloride is in red. So this shows that the cations have traded places. Okay, so here the cation, here the pure metal was copper, over there the pure metal is aluminum. All right, how do we spot this? You have, in this case, you have an ionic compound and a pure element, an ionic compound and a pure element. All right, so pretty easy to spot a single displacement. I mean, you don't have to memorize this ionic compound, pure element on both sides. You should be able to just look at it. You can draw this arc and see that it does that on the other side. It's a single displacement. Now, if we can substitute or displace the cation, can we do the same thing with the anion? In other words, can I write a reaction where we're substituting for the anion instead of the metal? And the answer to that is yes, and we'll take a look at that right now. Okay, so hopefully you have this written down, because actually, let's see, we can still do this. I would like to leave this up here if I have room. Let's see. Let's look at okay, and if I want to balance this, reactants and products. Okay, actually, I'm kind of running out of room here, so I'm just going to put the coefficients in. All right, let's see, I need 2 fluorines here, so 2 fluorines here, 2 sodiums here, so 2 sodiums here. So this is balanced now. Okay, this is balanced. Now, how could I write the general form of this? Well, first we see that it's the anion. We're drawing the arc on the anion rather than the metal cation. All right, so here, this is single substitution, but it's the anion being traded. So how do I write the general form of this? A X, oops, sorry. I want to do the X in red. AX plus Y gives us AY plus X. Okay, so we see there, in this case, it's the anion being traded rather than the cation. Okay, do we have any questions there? And again, if an ionic compound is made of both cations and anions, we should expect sometimes the cation will be the one substituted for, sometimes the anion will be the one that's substituted for. And that's exactly what we're seeing here in these two examples. Okay, do we have any questions? Again, notice ionic compound and pure element, ionic compound and pure element. Okay, any questions? All right, so we're all experts on now synthesis reactions, decomposition reactions, and now single substitution or single displacement. Okay, well, let's see. If we can substitute up here the metal cation and down here the anion, can we do both of them in one reaction? Can we substitute both the cation and the anion in just one reaction? And the answer to that is yes, as we'll see in this next example. So let's have a look at it. Excuse me. Let's see. Hopefully I don't run out of room here. Okay. So, we have these things here that we haven't seen before. These are what are referred to as phase labels. Phase labels. All right. So we can have S for solid, G for gas, L for liquid, or we have this AQ, and that stands for aqueous. Okay, so notice the iron hydroxide is solid. All right, the other three chemicals, the potassium hydroxide, the iron chloride, and the potassium chloride, are all aqueous. That means they are dissolved in water. Dissolved in water. So it's very rare that you have a reaction happen in a solid state. I mean, this would normally be a solid, a solid, a solid, and a solid. If I take these two chemicals as solids, mix them together, nothing. If I take these two chemicals as solids and mix them together, nothing will happen. But if I put them into water, stir them up and dissolve them, then I will get this compound. I forget what color that will be, but it will form a solid and sink to the bottom of the test tube or the beaker. Okay, so most of these reactions have to be in a liquid state. All right, so we understand what these phase labels are. We don't need them to balance the reaction. We don't need them to balance the reaction, but I just want you, excuse me, to get comfortable with seeing them. I can't remember. They might be on that assignment that I gave you. I think I may have taken them off though. But again, we don't need them to balance the reaction. So now we're going to do something a little different here. we need to balance this first, reactants and products. And if I take a look here, I see hydroxide ion there, OH. I also see hydroxide ion over there. So why not, rather than writing oxygen and hydrogen, why not just balance the oxygen and the hydrogen? Okay, why not do that? Okay, so that's what we're going to do. It'll be a little easier. So hydroxide is OH, and then we have iron and chlorine. Copy them in the same order on both sides. So what we're doing here now is effectively balancing ions rather than elements. Okay, so here I see one potassium. Cover up the potassium. I see that there's my anion, 2 elements. So I know it's polyatomic. There's just one of them. There's 1 iron and 3 chlorines. Over here I have 1 potassium, 1 chlorine, 1 iron. Cover up the iron. There's 3 hydroxides. If you don't feel comfortable doing that, then split up the oxygen and the hydrogen and balance the elements. By all means, split them up. It'll just take you an extra step or 2, but you'll get the right answer. Right? This is just a little quicker doing it this way. Again, if you don't feel comfortable doing it, just balance the elements. Okay, so let's take a look here. I don't have any pure elements, so I don't need to worry about that. I don't see any chemicals that are, any ions that are in 2 different chemicals on the same side, so I don't need to worry about that. I don't have the odd even either. Right? So let's just pick something. Well, let's see. Here I see 3 chlorines. Over here I just see 1. So I'm going to put a 3 here to balance the chlorines. 1 potassium times 3 is 3 potassiums. 1 chlorine times 3 is 3 chlorines. Okay, so the chlorines are balanced now. Now we screwed up the potassiums. They were balanced before, but they aren't now. So I'm going to put a 3 here. 1 potassium times 3 is 3. Now I'm going to cover up it. There's my 1 hydroxide. I cover up the metal. 1 hydroxide times 3 is 3 hydroxides. 3, 3, 1, 3, 3, 3, 1, 3. Okay? Now, as always, we should go back and check. 1 potassium times 3 is 3 potassiums. 1 potassium times 3 is 3 potassiums. There's 1 hydroxide times 3 is 3. There's 1 hydroxide times 3 is 3. There's 1 iron, there's 1 iron. There's 3 chlorines, there's 1 chlorine times 3 is 3 chlorines. So this is balanced properly. Okay, this is balanced properly. Okay, so let's erase this and see what class of reaction this is. Well, I had mentioned that we would do an example where both the cation and the anion were being substituted. So here I have an inner arc and an outer arc. Okay? Now, these arcs are drawn a little bit different than we did for the single substitution. So what's going on here? On the inner arc, the iron is going to pair with the hydroxide, which is what we see here. And on the outer arc, the potassium is going to pair with the chlorine, which is what we see in the first problem. Okay, so we have an inner arc and an outer arc, which is going to tell me how they're going to pair up on the product side. Okay, notice we always write the metal cation first. It's been a while. We always write the metal cation first in the formula unit for the compound. All right, so what's the general form of this? Well, first, this is called a double substitution or double replacement. Okay, and the general form is AX plus BY gives us AY plus BX. Again, the cations and the anions have traded partners. Okay, so we can draw those 2 arcs here. the inner arc and the outer arc. B and X go together over here, and A and Y go together here. And the metal cation in blue is always written first. Always written first. Okay, do we have any questions or comments? Any questions or comments? Everybody's a chemical genius. Jeez. Okay. So we have a couple more types to do. Next, we're going to take a look at a special case of a double substitution reaction. A special case. So let's have at this. Okay. Now, I mentioned that this was a special case of a double substitution reaction, so I should be able to draw an inner arc and an outer arc. Okay. The first thing I want to mention, this is already balanced. One hydrogen and one hydrogen, two hydrogens. One chlorine, one sodium, and one oxygen and one oxygen. Okay, so it's already balanced, so I don't have to spend time doing that. But I can draw an inner arc and an outer arc. The inner arc, the sodium goes with the chlorine. The outer arc, the hydrogen, goes with the hydroxide. So this is actually H plus and OH minus. All right, so two hydrogens and one oxygen give me a water molecule. So this is what is referred to as an acid-base reaction, acid-base neutralization reaction. Acid-base neutralization reaction. Now, I want to point out here what's really going on here. Remember, this is a very, very powerful acid. Very, very powerful acid. It's the acid in our stomachs. Okay, I mean, you could dissolve a lot of metals with that. You could probably dissolve a body with it. Sodium hydroxide. When I was a college student, my dad wanted his car painted. I had a bottle of that. It's rather inexpensive. I just put it in the water, got a paintbrush, painted it on my dad's car, and it blistered the paint right up. Okay? So again, dissolve metal or dissolve a body, peel the paint off my dad's car, mix the two together, and you get salt water. Salt water. Okay? You could literally drink it, although I'm not recommending that you do it, right? Because if you have these proportions wrong, you're going to end up dead. Okay? But in principle, a very toxic compound here, very toxic compound here, mix them together, salt water. So this is why it's called a neutralization reaction, because the toxic effects of the acid and the base are neutralized. Right? Now, how do I know this is an acid? How do I know this is a base? Okay, well, we talked in the third quarter how to spot an acid. It begins with a hydrogen, you cover it up, and if what's left is a recognizable anion from our periodic table or polyatomic ion list, then this compound is an acid. I'll say that one more time. All right? If a chemical formula, molecular formula, begins with hydrogen, cover up that hydrogen, and if what's left is a recognizable anion from our periodic table or polyatomic ion list, then this chemical is an acid. Okay, we also had the organic acids, but I won't give you any of those. Remember, they don't necessarily begin with hydrogen. They contain COOH. I won't deal with those. Okay, so now we know that this is an acid. How do I know this is a base? Okay, there's many, many types of base. We're only going to deal with one of them. A base is any metal hydroxide. Metal hydroxide, right? So you can think of it as an ionic compound where the anion is hydroxide ion. Any ionic compound where the anion is hydroxide anion, OH minus. Right? That makes this a base. So I have an acid, base, and then mix them together, the toxic effects are neutralized. Okay? Are we good there? Now, I want to point out something. I said this was a special case of a double substitution reaction. So let's have a closer look at that. Let's represent the universe of double displacement or double substitution reactions with a circle, Venn diagram. All right, so there's the universe of double displacement or double substitution reactions. Here are the acid-base neutralization. Now I have room to write it out. All right, so every acid-base neutralization reaction is a double displacement or a double substitution reaction. Okay, there's many, many, many other double displacement reactions. For example, the first one I did just before this one is not, it is a double displacement, but it was not an acid-base neutralization reaction. Okay, any question here? I should point out here that what's going on here is a proton is being transferred from the acid to the base. All right, OH minus is the base. This hydrogen is being transferred to it. Remember, H plus cation is a proton. So a proton is being transferred from the acid to the base to form water. Okay, so that's what happens in every acid-base neutralization reaction. Okay, any other questions? Any questions? All right, we'll move on to the next one then. All right. Everybody still there? Anybody else check in? Okay. I should have sent that email over the weekend. I meant to, but got tied up doing other things. So I did put PDF versions out there for you, Mr. Diego. Okay. Let's look at the next type. Okay, so we need to balance this, reactants and products. So AL and BR, copy them over in the same order on both sides. So here I have 1 aluminum and 2 bromines. Here I have 1 aluminum and 3 bromines. Okay, now, I do have pure elements. Normally we don't want to begin with those, but we have no choice. We only have 2 elements in this reaction, and both of them appear as pure elements, right? So we have no choice, right? Now, the aluminums are already balanced, 1 and 1. But here we have this even-odd situation with the bromines. So we know what to do with that, even and odd. We look for the lowest common multiple. The lowest common multiple of 2 and 3, 2 times 3 is 6. I'm going to want 6 bromines on each side. So I'm going to put a 3 here. 3 times 2 is 6, and I'm going to put a 2 here. 2 times 3 is 6. Okay, so now the bromines are balanced. Oh, I forgot the aluminum. That's a mistake people make. They only balance one of the elements and not the other. So here I have 1 aluminum times 2 is 2. All right, so now the bromines are balanced, but the aluminums are not. But I can easily fix that. All I have to do is put a 2 here. 1 aluminum times 2 is 2. 2, 6, 2, 6. All right, now let's double check. 1 aluminum times 2 is 2. 2 times 1 is 2. 3 times 2 is 6 bromines. 2 times 3 is 6 bromines. And we're good. We're good. Okay? All right. Now, we can see this is a synthesis reaction because there's only 1 product. Right? This A plus B gives us AB. 1 product, this is a synthesis reaction. But it's also another type of reaction, which is called an oxidation-reduction reaction. Oxidation-reduction. Right? An oxidation-reduction reaction. All right, now that's a mouthful. So what does this mean? What sort of reaction is this? This is perhaps the single most important class of reactions. All right, it is easily the largest class of reactions. Almost all chemical reactions are oxidation reduction. As a matter of fact, every reaction we have seen today, with the exception of the last two, which were double substitution. Double substitution reactions are not oxidation reduction. Okay, in an oxidation reduction reaction, and I think you're asked this on the assignment, in an oxidation reduction reaction, and the electrons are transferred from one atom to a different atom. Okay, we think about it. Metals give up their valence electrons to form cations. Where do those electrons go? To the nonmetals to form anions. Right? So that's what's happening here, and we can prove that. Again, electrons are transferred between atoms in oxidation reduction reactions. So let's have a look. Right here, there's no charges written up here. So I know this is neutral, and of course this is a compound. All compounds are neutral. So I can write Al with a neutral charge. I can write bromine with a neutral charge. And let's see, I have 2 of them. All right, or actually 6 of them. Actually, I'm just gonna write 1 of them. All right, I'm just gonna write 1 of them. Now, over here, I also have aluminum and I also have bromine, but they're not neutral because this is an ionic compound. So how can I get their charges? Well, I can look on the periodic table and I see aluminum's charges +3. It's a Roman numeral group 3A. Here, bromide is a Roman numeral 7A. So this is -1. Sorry, I lost you there. Okay, so we'll start that again. Okay, the aluminum is neutral. The aluminum metal is neutral. The bromine liquid is neutral. Here is an ionic compound. Again, we can find the charge on aluminum from looking at the periodic table. Roman numeral group 3 tells me the charge is +3. And bromide is in -7, 1 away from the nearest inner gas, so its charge is -1. It's a nonmetal, so it's negative. Right? The other thing we can do, if you remember, we can take the subscripts here and flip them and make them the charges. Take the subscripts, flip them, and make them the charges. So 3 is going to come to the aluminum, so +3. Here I have a 1 on the aluminum, that's going to be the charge on the bromide, is -1. So let's take a look here. All right, the aluminum started neutral, became positive. That means it lost electrons. It lost electrons. The bromine started neutral and ended up negative. That means it gained electrons. So what has happened here? The aluminum metal has given up its valence electrons to the bromines. Right? So electrons were transferred from the metal to the nonmetal. That makes this an oxidation reduction reaction. That happens in every oxidation reduction reaction. Okay? Now, any questions there? Now, how do you spot an oxidation reduction reaction? And when you're balancing, this should be the very, very first question you ask yourself when you're trying to figure out what type of reaction it is. The very first thing you should ask, do I have a pure element? If you have a pure element, that reaction must be an oxidation reduction reaction. It's very important. I'm going to repeat it another 1 or 2 times. If you have a pure element anywhere in the reaction, anywhere, then that reaction must be an oxidation reduction reaction. Must be. Okay? Does that mean all oxidation reduction reactions have a pure element? The answer to that is no, but the only ones I will give you will have a pure element in them. So in other words, we can draw another Venn diagram, the universe of oxidation reduction reactions. Right? And you draw a smaller circle, and I'm going to put PE for pure element. Okay? So we have many, many reactions that don't have pure elements in them that are oxidation reduction reactions. But the only ones we will be concerned with are these ones. Right? All of the oxidation reduction reactions we will see will have pure elements. So therefore, When figuring out the reaction type, that should be the number one thing you look for. Very first question. Then you worry about, is there one product or one reactant, or, you know, can we draw the one arc or things like that? Okay? All right. Again, this is the single biggest class of reactions, electrons transferred between atoms. All right. Now we're down to the very last reaction, very last reaction type. And it's actually a subset of the oxidation reduction. Okay, so let's have a look at that. Let's throw some phase labels in on this one. So these are all gas phase. All right. And let's proceed to balance this. So reactants and products. So carbon, hydrogen, and oxygen. Carbon, hydrogen, and oxygen. All right, so three carbons, 6 hydrogens, and 2 oxygens. 1 carbon, 2 plus 1 oxygen, 2, and 1 from the water is 3, and then 2 hydrogens. Okay, now, if we take a look here, we do have a pure element, oxygen, so we're not going to begin with the oxygen. In addition, the double whammy effect for the oxygen on the product side is in 2 different chemicals. So double whammy, pure element for oxygen and 2 different chemicals on the product side for oxygen. So we definitely don't want to begin with the oxygen. So what else can we begin with? I don't see any odd even, so I'm going to begin with the carbon. Right? I'm going to begin with the carbon. I have 3 here and 1 here, so I'm going to put a 3 here. 3 times 1 is 3 carbons. Now, how about the oxygens? 2 oxygens times 3 is 6, plus 1 from the water. Don't forget the 1 from the water. Okay, sorry, lost you there. So we put a 3 here to balance the carbon. So 3 times 1 is 3 carbons, 3 times 2 is 6 oxygens, plus the 1 from the water is 7 oxygens. Don't forget that 1 from the water. Quite often students will forget to do that. Okay, so the carbons are now balanced, and the hydrogens and the oxygens are not. We still don't want to do the oxygens until you have to. We don't have to because we can balance the hydrogens. Okay, so here I have 6 hydrogens and 2 here. So I need 6 hydrogens over there. So it requires me to put a 3 in front of the waters. 3 times 2 is 6 hydrogens, and 3 times 1 oxygen is 3, plus the 6 from here is 9. 9 oxygens. So now you see why we saved the pure element for last. The carbons and the hydrogens are already balanced, 3 and 6. All right? The oxygens are not. All I got to do is put a coefficient here and I'm done. All right? This is why you always save the pure element for last. When you can do it first, it'll just take you more steps to get to the right answer. You'll get frustrated and you'll give up. All right? Save the pure element for last. Now, let's take a look here. Whatever coefficient I put here is going to get multiplied by 2. And it has to give me 9 oxygens. Whatever coefficient I put here gets multiplied times 2, must give me 9 oxygens. So what number times 2 equals 9? What number x times 2 equals 9? Okay, what number times 2 equals 9? X is the coefficient that's going to go up there. Well, I got to solve for x. So I need to move the 2 over to the other side. It's going to go in the denominator. So x equals 9 halves. Leave it in fraction form. Don't put it in decimal form. Don't put it in decimal form. So now 9 halves times 2 is 9 oxygens. 369, 369. Okay, now we should go back and check, which we will do in a moment. But I want to point out one thing. if you were with me last week, this is balanced, but there is a problem. No coefficient should be a fraction. Okay? A properly balanced equation should not just be balanced, it should also not contain any coefficients that are fractions. So we got to somehow turn this 9/2 into a whole number integer. Right? We got to get rid of that fraction. Now, how can we do that? Well, I got to cancel the 2 in the denominator. So if I multiply by 2, for example, 9/2 times 2, the 2's cancel, equal 9. So by multiplying times 2, I can get rid of that fraction. But there's a problem though. It's already balanced. If I change this coefficient, it's not going to be balanced anymore. But I can take advantage of the second property of every equation, which is what you do to one side, you must do to the other side. What you do to one side, you must do to the other side. So if I'm going to multiply this coefficient by 2, I got to multiply all 4 of the coefficients by 2. Then it will still be balanced. Whatever I do to one coefficient, I must do to all of them. All right, so I'm going to multiply each coefficient by 2. All right, so I'm going to use green for this. So here the coefficient is 1 times 2 is 2. And I'm going to draw a circle around it so I know that that's my final set of coefficients. All right, 9/2 times 2, the 2's will cancel, gives me 9 oxygen molecules, 9 of them. Here I have 3 carbon dioxides, times 2 is 6 carbon dioxide molecules. And finally, I have the 3 water molecules, times 2 is 6 water molecules. All right, so 2, 9, 6, 6. Circles around so I know which ones are my final answers. All right, now we should go back and check and make sure that the equation is in fact balanced. So here I have 3 oxygens times 2 is 6. Or sorry, carbon. 3 carbons times 2 is 6. 1 carbon times 6 is 6 carbons. 6 hydrogens times 2 is 12. 2 hydrogens times 6 is 12. All right, so the carbons and the hydrogens are balanced. There's 2 oxygens times 9 is 18 oxygens. Okay, so here I have 2 oxygens times 6 is 12. So 12 oxygens, and 1 oxygen times 6 is 6. 12 plus 6 is 18 oxygens. This is a properly balanced equation now. Okay, always go back and check at the end. Because I'm going to tell you, I see this every year. Students will see this fraction here. Okay, sorry we're going out so much here. Students will see this fraction here, and they'll only multiply this one times 2 and forget about multiplying the other ones by 2. So if you don't go back and check this at the end to make sure that it's properly balanced, you won't catch that. And I feel so bad every year having to mark it wrong, right? Because they did balance it with a fraction, but when they go to get rid of the fraction, they do it wrong. They only change this one coefficient. Okay, instead of changing all 4 of them. All right, so we can see here, I'm going to erase this on the bottom. All right, now we're kind of crowded here. Here, let's get rid of the phase labels. Maybe that'll help a little bit. Okay, so here I see a pure element, so I know this is oxidation reduction. I know this is oxidation reduction. This is also what's called a hydrocarbon combustion reaction. All right, first off, it's a combustion reaction. Let's talk about that first. Oh, geez, we're out again. So first off, it's a combustion reaction. How do I know that? Because I have O2 on the reactant side. Remember, when something combusts, it burns, right? If you combust paper or combust a tree, you set it on fire. That requires oxygen to burn, right? To keep a flame going, right? So I have O2 as a reactant. Is that good enough? No. Whatever, the reaction must proceed very fast, on a very fast time scale. Right here, we're burning. So like if you burn paper, it happens very fast. The paper is burning. Okay. For example, if we look at this reaction, MgO, sorry. Okay, I think we may have done this back in the first quarter. You get a thin piece of magnesium metal and you burn it. And this happens very, very fast. If you remember, this burns very, very bright white light. Can't look at it, you'll fry your retinas, right? It burns super intense bright white light, right? This is a combustion reaction, right? You're burning something in the presence of oxygen gas. Is it a hydrocarbon combustion reaction? No, it is not, because we're burnt this right here. The other chemical other than the oxygen is not a hydrocarbon. A hydrocarbon contains just two elements, hydrogen and carbon. Hydrogen and carbon. So this top one is a hydrocarbon combustion reaction. This bottom one is just a combustion reaction, right? Just a combustion reaction, right? So is everything that have O2 in it, is it a combustion reaction? The answer to that is no. Let's take, remember, it has to happen on a very, very fast time scale. So let's look at another example. If I have Fe plus O2 gives me Fe right, so reactants and products, right? So iron and oxygen, and here's 1 and 2 and 2 and 3. So the oxygen is odd even, so I'm going to go balance that first, right? So lowest common multiple of 2 and 3 is 6. So I put a 3 here and a 2 here. 3 times 2 is 6 oxygens, 2 times 3 is 6 oxygens. It's also changing the iron. 2 times 2 is 4 iron atoms. I need to put a 4 here, and there we go. Now, I don't know if you've realized what's going on here. This is a piece of iron left outside, and it's rusting. It turns into rust. Piece of iron left outside turns into rust. Fe2O3 is rust. Right? Now, I'm sure that we all realize that when a piece of iron rusts, and that happens on a very slow time scale, you don't see a flame. You don't see a flame. So because this happens on such a slow time scale, this is not considered to be a combustion reaction, even though it has O2 as a reactant. Right? Even though it has O2 as a reactant. So when O2 reacts with magnesium, yes, that is a combustion reaction, even though the magnesium is metal. When O2 reacts with iron, it is not a combustion reaction. It is not. All right? So if I give you a reaction, how will you know if it happens on a fast time scale or not? The answer to that is you won't know. So if I give you one and it really is a combustion reaction and you don't say it is, I won't mark it wrong. Or if you say one is a combustion reaction and it's not, I won't mark that one wrong. All right? I mean, because there's no way, just from looking at the reaction, that you could predict whether or not it's a combustion reaction, with one exception. If the other chemical is a hydrocarbon, then it is a combustion reaction. Right? It is a combustion reaction. All hydrocarbons reacting with oxygen will ignite on fire and you get a hydrocarbon combustion reaction. Propane, for example, would be C3H8. Butane in a cigarette lighter. Butane, C4H10. Octane, one of the components in gasoline, C8H18. These are all hydrocarbons. They react with water. It happens very fast. Therefore, these are hydrocarbon combustion reactions. Okay, if you remember back in September, we said all hydrocarbons, modern society uses them as fuels, F-U-E-L-S, because they have a lot of chemical potential energy stored in their bonds. So when they undergo combustion, that chemical potential energy is converted into perhaps thermal energy, which can be used to cook our food or to heat our house. Okay, so let's take a look here. We said this is a hydrocarbon combustion reaction, hydrocarbon reacting with oxygen. It's also an oxidation-reduction reaction because we have a pure element here, pure element. So I know this is also oxidation-reduction. So let's draw our Venn diagram again. So here's our Venn diagram. There's the universe of oxidation-reduction reactions. Right? Now, some of them have pure elements. Some of them have pure elements. And some of the ones that have pure elements are combustion reactions. All right, I'm just going to write a C there because I don't have room to write it all out. All right, so all combustion reactions contain a pure element, O2. Since they have a pure element, that makes them an oxidation-reduction reaction. Okay, so electrons are being transferred between atoms here, even though these are all molecular compounds. Even though they're all molecular compounds. Okay, so again, one last thing. How do you spot a hydrocarbon combustion reaction? Well, you have a hydrocarbon reacting with oxygen. The products are always the same. I think that's a question on the assignment. What are the two products of every hydrocarbon combustion reaction? Carbon dioxide, CO2, and water, H2O. Two products of every hydrocarbon combustion reaction, carbon dioxide and water vapor. Right? The two products of every hydrocarbon combustion reaction. Okay. Do we have any questions? Because I'm done. Any questions? Any questions? Okay. I'm going to stop recording here and we'll talk about what we're going to do the rest of the week here. Let's see.